Okay, let's start today's class. And, good evening, one and all. I welcome you to the eighth live session of the NPTEL course, Production Technology Theory and Practice. So, in the previous 7 live sessions, we have come across different conventional machining processes, and we have discussed some numericals related to different machining processes, particularly turning, milling, drilling. Then we have come to grinding operation, which is essentially a finishing operation. Like after you have cast the material and you have done some preliminary machining operations like turning, milling, drilling, and all. Now you have to finish that. So for that you are doing this grinding operation. Along with grinding, there are different other finishing operations which we will slowly see in a few in today's lecture and a few in the subsequent lectures. And after that, we will be going into the unconventional machining processes. Okay, so I hope that you have gone through previous week's lecture videos and you have attempted the assignment as well. So coming to the first question for today's session. For a better finish in grinding, the grinding condition should be chosen to reduce the value of which of the following. What will be the correct option here? Okay. You're telling to reduce the value of depth of cut. So actually it is wrong. For better finish in grinding, you should try to reduce the value of chip thickness. See, chip thickness can't be reduced directly, like you can't give it as a parameter. Okay, but you have to choose depth, this depth of cut, then feed and the RPM as well as width of the this grinding width and all, so that ultimately the chip thickness is low. Okay, so they have asked for better finish in grinding. So so we know that during grinding the chip looks like this. Actually, this should be depth of cut only. I'm extremely sorry. Um, the chip thickness, it should if it's less, the consumption of energy will be higher. Okay. So yeah, the depth of cut should be less, and yeah, chip thickness it's not related anyway to this one. So yeah, you are correct. Actually, the depth of cut should be less. So this is my depth of cut, and this is the feed per unit revolution of the tool of the grinding wheel. And if you mention the feed velocity, then it's Vf. This is the rotational velocity. And this particular part here is the chip that is generated. Okay. I will try to come back to this question. I am a little bit doubtful about the options here, because if you reduce the feed velocity also, then also you can get a better finish. So I am thinking it should be chip thickness, because if this is the chip thickness, right? So somehow if you are choosing your parameters such that this thickness is coming smaller, then you are getting smaller chips. So the if the thickness is small here compared to a larger one. So in this case, you will get a better finish. You should be getting a better finish. So we will come back to this question after a while. Coming to the second question, which of the following circumstances increase the grain dislodgement during grinding? So if you zoom into a grinding wheel, you will see that the grains are embedded on into the surface onto the surface of the wheel, and some part of it will be protruding out. So these parts which are protruding out, they will be performing the cutting operation. These act as single point cutting tools. So they are responsible for material removal. So we know that in case this is the bonding material, and this is the abrasive or the grains that we say, abrasive 1 and 2. So in case my bonding material is soft, that is the grinding wheel is a soft grinding wheel, then while machining harder workpiece surfaces, workpiece materials, then the grains are easily pulled off, right? Because the strength of the bond between the abrasives, it is less than the strength of the material. Material means the workpiece material which you are grinding. That's why these grains get easily, you know, removed from the bonding. And as this grain is removed, so it is not that this particular place will remain empty. Behind this there are other grains, so that will get exposed and continue the cutting operation. So grain dislodgement is not a negative phenomenon as such, unless and until you are machining a soft workpiece. So while you are machining, say, aluminum, then if you are using a soft grinding wheel, then more grains will dislodge. So if the grinding operation won't be efficient, in those cases, while machining softer materials, we use a hard bonding material or hard grinding wheel, as we say. And in case of harder materials, like while grinding harder materials like mnemonic and all, we go for softer grinding wheels, so that these grains, after having performed the initial grinding operation, they get dislodged. Because if the grains don't get dislodged, after some time they will become flat, right? After some moment of grinding, they will become flat, so their cutting ability will be lost. So during this event, it will only rub over the surface, so that won't lead to any material removal. So that is something that we don't want, right? Because you are expending energy to rotate the wheel against the workpiece. So, but it is not performing any cutting operation. So that is inefficiency. So that's why in such cases you want the entire abrasive to come off. That is what we call as grain dislodgement. So to facilitate grain dislodgement, which of the following circumstances should be adopted, or rather, should be followed? What will be your answer here? Like, it is a multiple option correct type question. So what will be your answer here? Decreasing the feed force, increasing higher depth of cut, higher average chip thickness, using grinding wheel of less diameter and more width, and using higher RPM. So if you have gone through the lecture videos, you can relate this entire thing with the cutting force. So as the grinding wheel is rotating, so I have zoomed this and shown here. So this is my grinding wheel, and as it is being fed in this direction, it is producing some chip. It is removing the material in the form of chip. This is the chip here. Okay, so here the grinding wheel is exerting some tangential force as well as normal force at any point here along this contact length, as it is engaging say here along at this point, and it is disengaging here. So during this entire contact period, it is exerting the force radially outwards. So it has two components. One is that component which is this is the radial component, and another component is the tangential component. So the tangential component is performing the shearing operation by machining, and the radial component, it is exerting a normal force, right? So this normal force is basically indenting into the material or biting into the material, and the tangential force is removing the material. So that is how the material removal is occurring. So we know that this cutting force, the force which is responsible for the shearing action, it is directly proportional to the speed velocity raised to some power. I'm exactly not remembering the power. It's around 0.5, 0.8 or zero point 0.6 like that. Then your depth of cut to some power, that it is also in that this mn, they are less than 1. Okay, it's 0 0.4, 0 0.2 like that. Then grinding ratio to the power some power say p, and it is inversely proportional to the rpm to raised to some power x, then the concentration of grains raised to some power y, and the diameter of the grinding wheel raised to some power z. And also you have another term which is the unit specific energy, like the amount of energy which is required to remove unit chip width of the material. So if you carefully see all these terms, then you can realize that if this force is higher, if the cutting force is higher, then the chances of these grains to be dislodged from the wheel, it is higher. So chances of grain dislodgement is higher if your cutting force is higher. Okay, so how can you increase the cutting force in that case? Suppose you are having a soft, sorry, suppose you are having a, what is happening, sorry. Yeah, suppose you are having a hard material and your wheel is comparatively softer but not as soft so as to uh, facilitate the dislodging of these grains timely. So in that case, you have to tailor your processing parameters like feed force, depth of cut, all these things in such a manner that your wheel actually acts as a softer wheel. Like it is actually by means of strength, it is not actually a softer wheel, but due to the processing parameters, it acts like a softer wheel. To make it look softer, we have to tailor this particular parameter. So what are the parameters? If we increase the VF, that is the feed velocity, if we increase depth of cut D, if we increase the grinding ratio. So what is grinding ratio? It is the ratio of the width of the cut, maximum width of the cut divided by average chip thickness. So in this case, we can see that the chip thickness varies from 0 to T max. Okay, 0 to T max. The chip thickness varies from 0 to T max here. So the average chip thickness here is 0 plus T max by 2, which is basically equal to T max by 2. So B max divided by T max by 2 will give you the this grinding ratio gamma G. Okay. So VFD and gamma G, if they are increased, then you are having higher cutting force and higher chances of grain dislodgement. Whereas if you are reducing this RPM, if you are reducing the concentration of the grains, anyway, like if you fix a particular wheel, then you can't change, you can play with this C. So I'm I'm not considering this, and because this is not a process parameter, it is just the wheel property. And if you are reducing the diameter of the wheel, that also is a property of the wheel, then also you are increasing FC. So just correlate with the options here. Decrease feed force. Actually, feed force is you know it depends on VF. Like if you increase the feed velocity, then the feed force will automatically increase. Then so if you are decreasing the feed force, your FC will decrease. So this is not a correct option. Using higher depth of cut. So if you increase D, then your FC is increasing. So this is the correct option here. Higher average chip thickness. See here, chip thickness is T max, right? Maximum chip thickness. T max by 2 is the average chip thickness. So if you are increasing the value of chip thickness, your grinding ratio will decrease. But you don't want that, because if grinding ratio decreases, FC will also decrease, right? So this is not the correct option. Using grinding wheel of less diameter and more width. Yes, if you are increasing B max, which is the width of the cut, and if you are decreasing D, then your FC is also increasing. So this is the correct option. Using a higher RPM. If the N is higher, then FC is less, but you want more FC. So again, this is not a correct option. So your B and D are correct options here. Was this thing clear, or do you have any doubt? See, in the question, it is nowhere written how these particular parameters are related to the cutting force. Okay, so you need to understand that when you are being asked about grain dislodgement, then it has got something to do with the cutting force, because depending on that force only, these grains will either get dislodged or they will simply get glazed off, like they will become blunt, and it will lead to a glazed wheel. Okay. Moving on to the next question, which of the following factors are responsible for high specific energy consumption during grinding operation as compared to other machining processes? So as we know that compared to other machining processes, for a given depth of cut and given processing parameters, we have higher energy consumption, higher specific energy consumption compared to turning, milling, drilling. Grinding consumes more power. So what are the main factors leading to that observation? So smaller chip thickness, rubbing action between worn out grains and the work surface, plowing of the work material by sharp grains. Okay, so again, if you have gone through the lecture videos properly, then you can easily answer this question. I have already discussed what is rubbing action. When your grains, suppose this is the cutting edge of the grain, after some operation, after some period of grinding operation, it becomes blunt like this. So then its efficiency decreases, its ability to grind also decreases. So then what it does, unless and until it is being lodged off from the grinding wheel, exposing further grains, it will simply rub on the surface. So that consumes power. That is like not performing any cutting operation, however consuming power. So we know that specific energy consumption is nothing but power by MRR, right? So if there is no MRR, but it still is consuming power, then it is obviously loss of energy, and that leads to high specific energy, right? So in case of rubbing action, you have very low MRR, and you are consuming good amount of power, so that case leads to high specific energy consumption. That is the rubbing action, and it is being done by the worn out grains as it rubs on the work surface. Then coming to plowing action, so in case your grains are sharp, okay, so in that case, how does it remove the material? It deforms the material, and suppose this is the cross sectional view we are seeing, okay. So your actual feed velocity is either into the plane or out of the plane. Like this symbol, it represents that the feed motion is into the plane of paper. So this is your workpiece material. This is your abrasive grit. So these are the plow. This is the plowing action. Like due to this action, the work material gets chipped off and it deforms in both the directions. Again, it doesn't lead to significant material removal. It's just that it is indenting into the material. Now if it rotates, and then it will be performing the turning of sorry, grinding operation. So if you have carefully observed the ground surface, like after grinding, you will find these marks here. Okay, these are the grinding marks. They will be in, like it depends on the grinding operation. If it's finished grinding, then you won't be able to identify them. However, if you see this under microscope, a very small area, then you can see this. These are the grinding marks, and on both sides you have the plowed material which is sticking. If you take a cross section view, then it will look somewhat like this. So these burrs are coming off. This happens due to this plowing action. Okay, so that is again not much desired. However, it happens. It happens due to the inherent, process of grinding, inherent mechanism of grinding. So that leads to power consumption. And yes, the most important of all is the smaller chip thickness. Compared to like other machining operations like turning, milling, drilling, the chips that are involved here in case of grinding are very small, very small in size. Hence, the chip thickness is also very less. Since we know that in grinding, it just removes a few layers on the top of the material. So as a result, the you can understand that the chip that is formed here, it is very thin. So what happens in that case? If you look into the material aspects, then there are hardly any imperfections within that particular grains. If you look into the chip here, then you will hardly find any dislocations, or you will hardly find any imperfections. So hence, if it is a homogeneous material, then we know that it is having a very high shear strength. Its strength is very high. So even the number of grains here will also be less. Okay. To deform that material, it becomes very like you need to expend more amount of energy. So we can say that at lower cutting, sorry, at lower chip thickness, as the maximum chip thickness reduces, the energy required, the specific energy required, it increases. Okay, so it follows a graph like this. This is T1 max and this is UC. So it's somewhat like this. So at lower chip thicknesses, you can see the UC value is higher. At higher chip thicknesses, it is lower. Okay, so this happens due to the size effect. There are almost no imperfections within the material, and the shear strength of the material is pretty high. So option A, B, C, both all three are correct. So in this case, D will be the correct option. All of these. Okay. Coming to the next question, in centerless grinding, how is the longitudinal feed given while grinding long cylindrical workpieces? I hope you are familiar with the mechanism of centerless grinding. This is the grinding wheel. You have your workpiece supported here with the help of a blade. So this blade is just supporting the workpiece from below. It is providing a vertical support. That's it. And we have a wheel here. What is the name of this wheel? What is the name of this wheel? This is my grinding wheel. This is my cylindrical workpiece. What is the name of this wheel? No, no, no. This blue one. Grinding wheel is your this one, right? It is rotating and it is grinding the workpiece on this surface. This is called regulating wheel. What is the purpose of the regulator? You can see here. This is the actual pictorial view of grinding, centerless grinding operation. You can see this blue color here. This I think is the grinding wheel. This one here is the regulating wheel, and this is the workpiece, cylindrical workpiece. I hope you could identify. And this is that resting blade on which the cylindrical workpiece is simply resting. Okay, what happens? Your question is asking, suppose we have a longer, so along the length, if we want to grind, suppose this is the entire length of the workpiece and this is the grinding region, like at this portion it is grinding, so we need to feed the, your regulating wheel will be somewhat like this if you see a top view. So somehow your workpiece needs to be fed along the longitudinal direction to get it completely ground along the surface, along the entire length. So how is that done? Can you tell that? Yeah, can you tell that? Like how is this feed motion implemented here? Do we push it along this direction by applying a force, or is it being done manually? So actually what is done is we place this regulating wheel at a slightly inclined position. Now it is rotating. Actually, its diameter will be little bit, and this is your grinding wheel. Okay. So due to the regulating wheel, suppose the regulating wheel is rotating like this, the workpiece rotates due to the motion of the regulatory wheel, sorry, regulating wheel. So as the workpiece is rotating, the grinding wheel is also rotating and it is grinding the surface of the workpiece. Okay, so that's how it is being done. Okay, so coming to why it is inclined. So as this is inclined, so it is, as it is rotating, as the regulatory wheel is rotating, it is imparting two types of forces, like two components of forces at that point of, contact. So one is, so suppose this is the tangential force Ft. So it has two components, one along this direction and one along this direction. Okay. So yeah, suppose this is rotating like this, then the components of the force, like I have just marked it opposite. Okay, you can understand, I think. Like if the force is acting on this direction, the material will be fed in this direction. Similarly, if we rotate it like this instead of this way, then the workpiece will be fed in this direction. So what we do, what you need to remember is the regulatory wheel is not kept in line with the grinding wheel, rather it is being inclined at a particular angle. It can be, it is around 3 to 5 degrees. So due to this incline, the feed motion is getting imparted. So is it clear? Is it clear? Okay. Coming to the next question, thermal deformation during grinding due to high temperature can be reduced by which of the following methods? Increasing the wheel diameter, decreasing the depth of cut, increasing the feed velocity, increasing the wheel rotational speed, decreasing the concentration of active grains. So what do you mean by this term active grain? You can unmute yourself and answer, or you can also answer in the chat box, whichever is convenient. What do you understand by the term active grains? Obviously, with respect to grinding.
Sir, the grains which are participating in the grinding operation.
Yeah. So concentration is basically the number of such grains per unit area, right?
Yes, sir.
Hmm. Okay. Okay. So coming back to the question, so which of the following parameters, like well, which of the following options will lead to reduced thermal deformation or reduced temperature? As we know that grinding is being done at very high speeds, right? Compared to turning, milling, we are telling C is 2, 3, and 5. Decreasing depth of cut, increasing the feed velocity, and decreasing the concentration of active grains. Why do you think so? Like if you try to think it logically, anyway, you have a mathematical expression which defends your answer. But if you try to understand it logically, then what will be your explanation? Yeah, go ahead. I think you had unmuted yourself.
Sir, actually, I thought by the formula way, we had the formula, and by that analysis, I gave the answer.
Okay, that's fine. But if you try to think it logically, like by the physics of the process, then what happens? If you are uh, so if you go by the first option, like increasing the wheel diameter, so say for this depth of cut, this is one wheel, and for the same depth of cut, okay, this is a little more smaller. So suppose this is another wheel. Okay, in both cases, if you are imparting the same feed motion, that is after some time, say your wheel is moving by this much distance, here by this much distance. So this is the chip in one case, this blue colored one, and this violet one is the other one. Sorry, the purple one is the other chip. So what difference can you notice between these two? Visually, what is the first observation? So you can see that the length of the area of contact, where the length of the machining length, that is smaller in case of smaller diameter wheels, right? Correct or not? This is smaller as compared to this one. So if you are reducing the contact length, then obviously the temperature should be reducing, right? Because at any point of time, only this much of the wheel is in contact. The aerial, the aerial contact, that area is also reducing. So as a result, the first option is incorrect, because if you increase the wheel diameter, more will be the length of contact, and that there are more chances of uh, thermal effects coming into picture at high temperatures, right? So anyway, the first option is getting eliminated. The second option, decreasing the depth of cut. Again, if you decrease the depth of cut, you will see that. So I'm showing it here itself. Suppose this is another case. Okay, so this is one depth of cut, and this is the second one. Okay, so in one case you can see that so in which case your chip thickness will be less. In which of the two cases do you think that the chip thickness will be less? For the blue one or the purple one? So you have chips. If you try to see the chip morphology, you have two chips. One is getting restricted up to this one due to lower depth of cut, and one is up to here due to higher depth of cut. And this is the baseline or the reference line. So here obviously the chip thickness is less, maximum chip thickness, compared to here. You can visually identify, right? This is more, this chip thickness, and this one is less. So as a result, what happens? If you are decreasing the depth of cut, your chip thickness is getting reduced. Okay. So as a result, the temperature effects will also, like temperature, due to high temperature, the thermal deformation will also reduce if you are decreasing the depth of cut, because your chip, this first of all, the contact length is also reducing here, that I forgot to mention. So this was your contact length in one case, and this is the contact length for higher depth of cut, right? So your contact length is also reducing if you're lowering the depth of cut, as well as your chip thickness is also reducing. So due to this cumulative effect, your thermal deformation due to high temperature is reduced if you are decreasing the depth of cut. Okay. Increasing the feed velocity. So the third option is increasing the feed velocity. So how is feed velocity affecting the temperature, like thermal effects? So I'm writing that expression, the mathematical expression here, just for better understanding. Okay. So here you can see that theta is inversely proportional to Vf. So if you are increasing Vf, then your theta will decrease. So as the temperature reduces, the thermal defects, the occurrences of thermal defects will also get reduced automatically. But why? Why? To answer that, again you have to see here. Okay. So this green one is the initial position of the wheel at any instant of time. So for higher feed velocity, this magenta colored one, this depicts a higher feed velocity, and the blue one here, it depicts the lower feed velocity. Correct. And as you know that the wheel is rotating. So you can see that in case of higher feed velocity, you are getting your chip like this, while in case of lower feed velocity, your chip is somewhat like this. So what actually happens here? So you know that the temperature theta, it's directly proportional to the energy per unit time per unit area, surface area, right? So if you see that surface area, then it's basically the width of the cut b multiplied by the feed velocity vf, right? If you try to expand this, I am erasing this part. So energy per unit time is nothing but power. So you can write it as power means basically your specific energy into the MRR. MRR is VF into width of the cut into depth of the cut divided by 60. If your VF, this is given in meters per minute. Okay, divided by area. So area is nothing but width of the cut into VF, feed velocity. So here BVF, they will get cancelled out. Basically, it will be left with D into UC. Now, if you expand this term UC, you know that it's basically U naught into average chip thickness to the power minus zero point 0.4 or 0.6. I think minus 0.4. So if you also know that like what is T1 max. If you have gone through the derivation, then it will be easy for you to identify what is T1 max. I don't have the final expression with me now. Okay, it's this 4 VF into D divided by. Okay, so this is T1 max to the power minus 0.4. So if you just substitute it here and simplify, then you will get that final expression that we had written on top, this one. So here you can see that this VF, it's like if you are increasing VF, your T max is like this T1 max is this average chip thickness is reducing, right? If you are increasing VF, then your average chip thickness, average chip thickness is increasing, but since it is raised to a negative power, minus 0.4, this entire green box that I'm marking here, that is reducing. Correct. So that is reducing. As a result of that, UC is reducing and hence theta is reducing. So that should be the argument here. Like here you can say that okay, like my chip area is more, so the chip thickness is more, so my power consumption it's less, and hence we can defend the argument by saying that my thermal decomposition, sorry, the thermal deformation will be lower due to lower increase in temperature, since the energy expended for the shearing action, it's less for higher chip thickness. But how do you actually arrive at that? For that you need to go through the derivation. Only then you can identify, okay, so you have got another VF term on the top due to the MRR. So MRR is dependent on the feed rate. So if you increase the feed rate, your MRR will increase. But but that is getting cancelled out by the VF and in the denominator. So this VF corresponds to the area, like per area of the machining. So okay, so increasing the feed velocity decreases the temperature or the thermal deformation effects. Coming to the next one, increasing the wheel rotation speed. Again, if you can see here, if you increase the wheel rotation speed, then your T1 max will reduce, right? And as a result of which, this entire blue colored box, since it is raised to a negative power, it will increase if you increase n. And as a result of that, your specific power consumption will increase, and hence the thermal deformation effects will increase. But if you try to think it logically, then also you can arrive at this conclusion that if while you are increasing the speed, the power consumption is more, right? So that power is being, that the power that is required, that is expended during this machining operation is more. So that power is leading to more amount of heat dissipation, more amount of heat generation at the interface between the grinding tool and the grinding wheel and the workpiece. So at higher RPM, that's why your temperature will also go up. And since we know that grinding is done at a very high RPM, so generally the temperature at the interface, it may rise up to more than 1000 degrees Celsius also, which is very high. But why doesn't the workpiece material melt? Can you tell me, like, why it doesn't melt, even if it goes much beyond the melting point of the actual bulk material? Why doesn't it melt? What happens? Suppose this region where the chip is getting formed, here the temperature reaches around 1000 degrees Celsius, but that happens only for some fraction of seconds. Yeah, so that happens only for a fraction of seconds. So this region which should have been melted, it is not getting enough time to reach that particular temperature and get melted. I'm talking about the workpiece material. Okay, so due to the high speed of the grinding, it doesn't happen, this melting. Okay, then the last option, decreasing the concentration of the active grains. So as you can see here, if we increase the concentration of the grains, again this T1 max, that is the maximum chip, or rather the average chip thickness T1 max by 2, that will reduce. And if that reduces, something like when it is raised to the power or negative, raised to a negative power, then that entire thing will increase, right? So it increases means theta will also increase. And if you try to think it logically then also if the number of grains per unit area is more, then there is more interaction between the grains and the surface of the work material, and as a result of which the temperature increases further compared to when you have very sparse concentration of grains. It is also logical that when you have a sparse concentration, if the concentration of the grain is less, areal concentration, then your work, this material removal rate will also reduce, but the temperature, the heat generated will also be less, and the temperature in that region will also be less, and as a result of that, thermal deformation will be less. So we see that option 2, 3, and 5 are the correct ones, I think. Or shall we just check once? Decreasing the depth of cut. Here, decreasing the depth of cut, increasing the feed velocity, decreasing the concentration of active grains. Okay. So there are other parameters also. You can just think about them, like the grinding ratio, which is nothing but the width of the cut divided by the chip thickness, average chip thickness. So your question can have options related to other parameters also. So accordingly, you need to choose the correct option. This is the last question for today. Match the following with respect to grinding operation. So fracture wear. So these are related, these three types of wears, first three. They are related to how wear takes place in a grinding wheel. Correct. So you can unmute and tell your answer. So fracture wear is nothing but
Sir, crumbling and
setting
flattening
of
of
the
sharp
abrasive
abrasive
grains
edges.
under high stress concentration. Yeah, come again. It was not audible. Hello.
Sir, chipping of the abrasive grains under high stress condition.
Yeah, that leads to fracture. So what happens? So basically, as the name suggests, suppose this is one abrasive, so it gets fractured from here or here. So due to this fracturing, what happens? The entire grain is not dislodged. The grain entirely is not dislodged from the wheel. Rather, a part of it is dislodged and the rest of it is still exposed. Suppose this green part, this is the fracture line, say, or this particular part. So this part is still exposed and they can continue with the cutting operation. And after some time, then it either will get dislodged or will get flattened out. Okay, so that is fracture wear, and it happens when obviously there should be huge stresses generated, huge stress required to fracture the grain. It is a hard phase. So to fracture it, you need large amount of stress values. So it is logical that it occurs under high stress condition. Then atresia wear. When does it happen, or what is it basically? The atresia wear is when during the initial phase of grinding, when the tips of this sharp edges of the grinding, sharp edges of the abrasives, they get chipped off and become flattened. Okay, like this. So due to this, rubbing action will be more, and hence the temperature will also increase, and all those things will all those temperature related deformation and other things will get aggravated. So that is atresia wear. It's the crumbling and flattening of the sharp abrasive edges leading to pronounced rubbing action. Bond post fracture. So that is basically bond post is As we know, tool post, like the tool post holds the tool. Similarly, the bond post holds the abrasive. So this is your bonding material and this is your abrasive. This is the bond post. So suppose this, but it is failing over this region or at the interface between the bond and the abrasive. So then we term it as bond post fracture. So this entire thing is getting separated out. This entire abrasive is getting separated out. So this happens mostly in case of soft wheel when you're trying to machine a hard material. So that is nothing but the dislodgement of the abrasive grains from the wheel. Now coming to two more finishing operations, which are abrasive based finishing operations, like you are employing abrasives to remove material from the surface, but they are different from grinding. So honing and lapping. So which options do they correspond to among the remaining one? So you have this one and this one remaining. So which one does honing correspond to?
Sir, honing is soft finishing operation.
Honing, as you know, yeah, you're not audible.
Sir, soft finishing operation.
That is honing, you're telling.
Yes, sir.
Honing is not soft finishing operation. Lapping is soft finishing operation. Honing,
Okay.
honing is done. They've seen your honing tool looks like this. There's a vertical spindle sort of thing, and then you have the honing tool. So here you have abrasive pads arranged circumferentially. So on these pads you have abrasive grits lined over it basically. Now suppose you're trying to finish the internal surface of a bore. So suppose this is your cylinder. So you are trying to finish the inner surface of the cylinder, internal walls of the cylinder. So what do you do? It will be till here. Sorry. So what do? You impart a reciprocating motion as well as a rotary motion to this tool. Okay, and this rotary motion is not in a single direction. It as the tool is moving upwards, it is say moving and clockwise, and then it is as it is going downward, it is moving anti-clockwise. So as a result, if you see the surface, the texture will be like this crisscross pattern. In grinding, it is in single direction. Like single pass of grinding, if you do, you will get the grinding lines like this. If you are performing a honing operation, you will the surface texture will look like this. Okay, so it is basically done at like very less speed as compared to grinding. Grinding is done at much higher speeds. Then soft finishing operation is basically lapping. So you have a lapping tool which is softer than the workpiece material. And how do you prepare that? You take a grooved surface, you put some abrasive powder on to it, and then you put some mineral oil, and then you rub the workpiece in a designated this infinite sign like fashion, or some other loops. You don't rub it in a definite direction as in case of grinding or polishing. Here you do it in random loops. So what happens, the surface get finished. So that is lapping. That corresponds to a soft finishing tool, and honing is done at lowest cutting speeds. Okay, so that's it for today's class. Anyway, the questions were pretty simple, and they were mostly straightforward questions. Just be careful about this type of questions where you have to correlate the parameters. Okay, you need to identify, like, say in this question, if you directly conclude from this particular line, say theta, we know that temperature is directly proportional to the energy per unit time. So that's nothing but your specific energy into MRR, or the power. It is energy per unit time is power. So that's nothing but the specific energy into MRR. So MRR, as we know, is directly proportional to VF. So essentially, theta should also be directly proportional to VF. If you would have drawn such a conclusion, then your answer would have been wrong, because you need to know that it's also inversely proportional to the area. So it is directly proportional to the energy expended per unit area. If you are increasing the area of machining, area means how much area you are machining, say VF into the width of the machining. So VF is nothing but the feed motion, distance traveled per unit time, into the multiplied the width of the grinding wheel, or the width of the grind like cutting, width of the cut. So that area, if it's higher, and the energy which is expended, or the power which is expended per unit area, if that P is constant, say, and if this area is larger, then only you can ascertain that theta will be less, right? Okay, so these are few things that I wanted to discuss. If you have any other doubts, you can tell now, we can discuss. And yeah, you should also practice some numericals based on, you know, the mechanics of grinding. Like, suppose you are given to calculate the MRR, or you are given to calculate T1 max. It's always better to learn the sequence of derivation, like how you are arriving at T1 max. I hope that you have gone through that derivation. So you should at least know the steps, like how you are arriving there, so that in case you are not sure about any one of the particular powers, say here you have d raised to power 3 by 2. Suppose you are skeptical about this one. So in that case, you can just do the derivation quickly and arrive at this correct exponent. So those are the things. Yeah, do you have any other doubt?
Sir, for practice, you have suggested three authors' book. So shall we do all the example questions or the unsolved questions also?
See, the more number of numericals you practice, the better you will be at it, right? The
Yes,
better,
sir.
yeah. So it doesn't like I shouldn't be mentioning how many problems you should practice. Rather, you try to follow the questions, like how they are. Don't practice same type of questions. Okay, you should practice different type of questions. There should be variety in the question. Suppose in grinding itself, questions can be framed from different topics, from mechanics of grinding, from the power consumption point of view, from this temperature point of view, cutting force point of view. There can be so many type of questions that can be framed, and also number of passes and all. So you should practice different types of problems. So that is more important. And yeah, the books that I have mentioned, that is this AB Chattopadhyay and Ghosh and Malik. So this is not just for grinding; it's for the entire syllabus, for entire machining. I'm telling.
Yes, sir.
And Sirop Kalpakjan. Yeah. So I'm not asking you to purchase all three books or get all the three books. You can stick to any one. But as you go through one particular book, you can understand that there are some shortcomings. So you need to probably refer to some other book. Suppose this particular book, Sirop Kalpakjan, it is good in theory. If you want to build a good theoretical background in manufacturing, then this book is good. If you want to look into analytical modeling of the processes. Processes means any process, say from casting, welding, grinding, anything, even forming. Then Ghosh and Malik is a good book. It may be a bit difficult to understand in the beginning, but if you try to follow the steps carefully, then it is a very good book. It is a small book. You can see it is yellow in color. And particularly for machining, I would suggest A.B. Chattopadhyay. Okay, for this turning, all these things, turning, milling, grinding, drilling, all these things. So you can see here that the syllabus that have been covered in this particular course, that is just a subset, because that is not intended for masters or PG level students, right? That is for BTech level students, this particular course. But the same course can be designed for a postgraduate also. So I had learned this course in BTech also, and even during PhD, I had during the coursework I had learned this course. So there was hell and heaven difference between the curriculum of both. So that's what, if you go through this particular book, you can understand that there's more depth into what we are just doing now, what we are studying now. Okay, so that's it. Any other things you've addressed?